Hi everyone, this is the internal energy and specific volume video. So you've heard these terms before since we've introduced the first law of thermodynamics, but let's dive a little bit deeper into what specific volume is and then internal energy and its relationship to enthalpy. So we just introduced enthalpy, a fresh new topic here. We also introduced entropy. This one we're going to focus on enthalpy. So let's talk a little bit, what is specific volume? And all specific volume is, oh, that's the wrong marker. Let's try this one. There we go. Specific volume is just simply a volume. We talked about specific in a previous video and what that means. So volume per unit mass. So what does that look like in terms of an equation? The specific volume, which this is the Greek letter nu, so lowercase nu is what that's called. Again, confusing, another V, volume, velocity, specific volume, all the things. But that looks like volume per unit mass, which that should look somewhat familiar. You're like, I've seen these variables. If you look at what the density is, which remember this is rho, Greek letter rho, that's equal to mass per volume. So when we look at terms of units here we have basically like a meter cubed per kilogram, or a foot cubed per pound mass, or something like that. Whereas here we have something like a kilogram. Actually, let's use English units here since we didn't on the other one. Let's use pound mass over meters cubed. So if we combine, actually let's stay with blue. Let's do pink again. If we combine these two equations together, we get that the specific volume is equal to 1 over rho. So easy ways to be able to find that. And you can kind of think about that relationship of, I want to know how much volume I'm going to take up per unit mass. In density, I want to figure out how much mass I take up per unit volume. So it just depends on what you're using. In thermo, we focus much more on per unit mass because then we can scale accordingly. Think about a power plant. If I put in 1 gram versus 10,000 grams versus 1,000,000 grams, how is that going to scale? Versus in fluids, I was more concerned about, well, if I put 1 gallon in versus 17 million gallons in, we would scale that way. So thinking a little bit more about applications here makes sense that we use specific volume in thermo. We use density and specific weight a lot more in fluids. So where do we use this? One of the biggest ways that you just saw in a previous video is that H is equal to U plus pressure times specific volume. So let's talk about what that looks like and what its relationship is. So we have seen now a TS diagram, which is a temperature entropy diagram. And the nice thing is you'll also see P V diagrams, which we say V, we really should say P nu diagram, so that's pressure times specific volume. And the nice thing is that the relationships between temperature, well, I guess on this x-axis really, is that both entropy and specific volume have a similar relationship in the sense that if we are to look at a line on this diagram, so looking at, we have a working fluid going through, and we start out at a subcooled liquid. I guess I can leave that. Subcooled liquid. We get up here to a saturated liquid. We're here in the wet vapor zone. We're here, I should have marked these. Those are the points I'm talking about. We're here at the saturated vapor point, and then up here we're at a superheated vapor. These relationships are going to be similar, that as I go up this line and transition from a liquid to a vapor, my specific volume is going to increase. And same thing with entropy. If I was to do entropy at each of these points, those are also increasing as I'm moving from left to right on my temperature entropy or pressure specific volume diagram. So you'll get a lot more comfortable with these as we get more practice, but just wanted to show that relationship. We do follow the same trends for entropy and specific volume there as we follow the line. Okay, so let's go to a couple of examples, because sometimes in thermo books, or when you see equations, wherever you're finding them, that sometimes heat transfer, so Q, is referred to as delta H, so your change in enthalpy, and sometimes it's referred to as delta U, or delta internal energy. So we talked a little bit about internal energy on the first law of thermo video, but let's talk out when we use one versus the other. So what I want to start with first is, you can pause the video here and walk through this, but write out that first law equation with regards to rate. So remember, we had a rate equation that we did. It has the dots, so I'm going to give you a second, write that out, and then we'll work through it here. Okay, hopefully you're back. But thinking about that equation, we have Q dot in minus Q dot out plus work dot on minus work dot by. And then we have plus your mass flow rate in times all of the things that it brings with it, which is potential energy in plus kinetic energy in plus internal energy in, or that's enthalpy, because we combined the types of work and put internal energy into that. So that was the last video. My mistake there. We've already combined those. And then we have mass flow rate out times potential energy out plus kinetic energy out. Oh no, I didn't leave myself enough room. Plus H out is equal to 0. So we know that because of the first law of thermo, the conservation of energy, this has to be true. It has to be equal to 0. Everything has to balance. So let's think about, if we have a boiler in a Rankine cycle, we have some sort of mass flow rate coming in, and that is some sort of liquid coming in. And then we have some sort of fluid coming out, which is a vapor, lots of times a superheated vapor, but some sort of vapor. This marker is probably not the best. And so we have a liquid going in, a vapor coming out. If we are trying to find how did we make this phase change happen, we know that we had to put some Q. Oh, I'm back to the crappy marker. I need to throw that one away. So I keep picking up Q in to be able to make a phase change happen from a liquid to a vapor. So if we are to simplify this equation, we know we have Q in. We're not going to have any Q out. We don't have any work on. We don't have any work by. We do have mass coming in, and we know that in thermo, that mass coming in, the potential energy and kinetic energy really aren't changing between point A and point B, so we neglect those. And same thing here, we keep the H, but get rid of the potential energy and kinetic energy. So what does that look like in an equation? I'm going to come back. I'm digging this blue marker, not the yellow one, so we can write a little thinner here. So we have Q dot in. So the Q that we need to transfer in to make this phase change happen is equal to the mass flow rate times delta H, because we know that it has a certain H coming in, it has a certain H coming out. So let's think about the relationship, though. Let's go over to this of H equals U plus PV for a boiler. We're actually going to do this for something else as well. So I'll label this one boiler. When we go through this phase change, the U, the internal energy, you are increasing the temperature, you're adding a bunch of energy. So your internal energy of this fluid, again, remember this is the mass flowing in, the actual energy in that fluid, internal energy, is going to increase. Does the boiler really change pressure? Not really. And that's where you can see this. This is our constant pressure line. As we're going from this phase change of a liquid to a vapor, we're not really changing pressure. You can see that on a pressure specific volume diagram. That one's obviously a temperature pressure, but we're keeping a constant pressure throughout this system. So we're going to call this neutral. It's not really changing. And then our specific volume, based on what we just saw here, our specific volume and specific volume here, we actually make quite a big change. So we know that our specific volume is also increasing. So we went through a phase change in a boiler. We want to find Q, so our ultimate equation here, now after we have said this, is going to have to be Q dot in is equal to your mass flow rate times your H at the vapor is going to be higher. So this is going to be, we call that the H out minus the H in, which is going to be lower. It doesn't have as much energy. It's in liquid form, so the H is a little lower. So in order to get a positive Q of we are transferring this Q into the boiler, this is the equation that we're going to use because H out is the higher energy. Okay, so in this, we had to consider both internal energy and flow work, which includes our specific volume, because there are pretty drastic changes in your specific volume and your internal energy because of all this Q that you're putting in. But let's look at a case here with a heat exchanger. So if you're not familiar with what a heat exchanger is, a boiler is kind of a heat exchanger too, but we're going to look at one here. This is like a tube running through a system, and we are going to put some sort of liquid in here that, let's say it is a lower temperature. So this is low temperature, and we're trying to get it to come out at a higher temperature. And so this fluid that we're putting in over here is going to, whoops, let's put higher temp. It comes in as a low temperature. You're trying to get it to leave at a higher temperature, which means that this fluid over here has to come in at a higher temp and come out at a lower temp. So this is a heat exchanger. We are transferring Q from one liquid to the other, from one liquid to the other. Higher to lower is the way that heat energy transfers. So let's think about if we focus on this fluid that is going through this pipe, so moving through, and it is gaining energy from the fluid that is flowing through this system. I should probably use a different color because you have some sort of liquid going through here that is contacting all of this pipe, causing the heat transfer and then eventually going out. We're focusing on this blue liquid, which I'm going to take this one off. Probably not the best erase job, but I'm going to take this one off. So the blue liquid is being affected by the pink liquid. So what does that look like in terms of H equals U plus P B? Excuse me. So thinking about we are transferring Q from the higher temperature liquid into here. So you have a Q in. And so this blue fluid is still gaining energy. So our U is increasing. Is our pressure really changing in a heat exchanger because we are not going through a phase change? Excuse me, and we are not pressurizing this in any way? Again, no, it's staying pretty much the same. Our specific volume, we are basically going from a subcooled liquid maybe down here to a subcooled liquid here. So is our specific volume really changing? Not really, because we're not going through a phase change. Because remember, our phase change here going from liquid to vapor, we've got a lot of change in V, whereas here we don't really change V very much. We don't change the specific volume. Sorry, I've got a tickle in my throat. So for the case of when something is not going through a phase change, our specific volume isn't changing much, our pressure isn't changing much, we can say that delta H is about equal to delta U. So this is where the assumption comes in that you may see in a thermo textbook or on a website or something that delta H and delta U can be the heat transfer. So in this case, our equation could look like Q dot N is equal to the mass flow rate. Again, that's the mass flow rate of this one, the fluid going through, not this one. You could do a calculation on this, and it would just be negative compared to the other one. So it's losing. Q out of the pink fluid is Q into the blue fluid. Times U at the outlet is still higher because it is more energy. It has had Q in, minus U at the inlet. So you can see now the difference between these two. They're similar in the sense that the outlet is higher energy than the inlet, but there's not a phase change happening. So we can also say that the internal energy is similar enough to the difference in the enthalpy between the beginning and the ending that we can use either. So there you go. That is specific volume and internal energy, specifically looking at the relationship between internal energy and enthalpy.